In today's lesson, we are going to learn about piecewise functions. Before we begin, I must let you know that you must have a pencil with an eraser for this lesson. If you happen to have an erasable pen, if it works really well, you can use that. But stop this video now, get those materials because we will need the eraser for part of what we are doing today. This first little piece here is not in your note packet. I'd still like you to follow along. It's just a little situation that we're going to talk about to help set up this idea of piecewise functions. So we're going to consider this story where we have a woman that starts at her front door. She walks to her mailbox, stands there for a while, gets the mail, and then returns to her front door. We're going to think about what the graph of this scenario would look like. So on the x-axis, we've got time in seconds. On the y-axis represents the distance away from her front door. So as she's walking toward the mailbox, time is passing by, so we're moving forward. The distance away from her front door is increasing, so we're going up. Now, when she stands at the mailbox, time is still going to pass by, so we end up with this flat horizontal line where her distance from her front door is not changing because she's just standing there. Finally, when she walks back to her front door, the distance away from her front door is getting smaller, so it's decreasing. We're actually going to have a line going down here, ending back where we started. So we can see here that some functions are in pieces, and they are called piecewise functions. Now, if we were wanting to write an equation for this that would produce a graph that has these three different parts, we would need to see that we have three pieces that has a different equation defining where it is. So there would be an equation defining this first part that's increasing. That would be something with like a positive slope. We would have a different equation for this middle part that's just a flat horizontal line that actually has a slope of 0. And then we would have a different equation for this last part that's decreasing. That would be something with a negative slope. So continuing on our note sheet, we're going to see that a piecewise function is composed of two or more functions which each define a piece of the new function. To build our first piecewise function, we're going to graph each function below separately. Notice that we have the function notation here, f of x. That's just another name for y in this case. So when it says to graph f of x equals 3, we're really graphing the line y equals 3. And anytime we have y equal to just a number, it's really the situation that has a slope of 0. So if we think about slope-intercept form, it's really like 0x because 0 times anything is 0. That's why we're only seeing the 3 on the end. And remember that when we have a slope of 0, it's going to be a flat horizontal line. In this case, it's just passing through the y value of 3. So think about the y-intercept of 3 right here, but then when we go to draw our line, it's just a flat horizontal line across like this. Y equals 3 for every single x value. That's why it looks horizontal. Now we're going to graph another function, g of x equals x plus 2. We can also think about this as just being y equals x plus 2. This one has a slope of 1, which is the same thing as 1 over 1, and it has a y-intercept of 2. So let's go ahead and start by plotting the y-intercept of 2. It's a positive slope, so it's increasing from left to right. We're going to go up 1, over 1, up 1, over 1, up 1, over 1. Continue the pattern for a few points in the opposite direction, and we'll go ahead and connect them. That is going to start here. There we go. It will now be useful for us to consider different ordered pairs on the graph of each function. We're going to fill in the tables below with information corresponding to the above function graphs. So for our first table, this is when f of x is equal to 3. When x is negative 6, the y value is 3. When x is negative 5, the y value is 3. When x is negative 4, it's 3. The y value is always 3. That's the whole point of the function f of x equals 3. So that one was easy to fill out. For the next one over here, for g of x equals x plus 2, I copied over the graph just so that we can see it here. When x is negative 2, we can see that the y value is 0. So this is really asking for what the y value is. When x is negative 1, y is 1. When x is 0, y is 2. When x is 1, y is 3. When x is 2, y is 4. When x is 3, y is 5. And finally, when x is 4, y is 6. So now we're going to trim each graph at the very beginning to only look at one piece of it. We're going to erase each of the above function graphs so that each function is only covering the x values listed in the tables that we just filled out. So for the first graph, we're only going to show the part that is x values from -6 to -2. So let's go back to this graph at the very beginning. Grab your eraser. I'm actually going to use my highlighter here first to show that we only want the graph to exist for x values from -6 to -2. So I'm going to grab my eraser and erase the rest of it here. Okay, now for the second graph, this table was for x values from -2 to +4. So I'm going to grab my highlighter again and start this at the x value of -2 and highlight all the way up here to the x value of +4. I'm going to grab my eraser, and everything to the left of -2 is getting erased. So now we're going to consider what it would mean to graph them both together on the same coordinate grid. We're going to transfer those pieces to the coordinate grid below, being careful to place them where they belong. So I just did a little snapshot of the graphs that we just did so that we can look at them all together here. So for this first piece, it's going to be from -6 to -2. And it's going to be at the y value of 3. So the first part is going to look just like that. I'll highlight it again to make it kind of stand out. Notice how that's matching where we have the line graphed in the first picture to the left. Now we're going to transfer this piece over onto the graph. So it's going to start when x is -2, the y value is 0. It's going to end when x is 4, the y value is 6, and I'm going to grab my line tool and just draw a straight line connecting that. Use my highlighter tool again to make that stand out, so we can see that we literally just took that piece and transferred it over here so that it's on the same grid as the first piece. Now we're going to think about whether or not the graph we just constructed is a function. Well, if we think about the vertical line test as an easy way to see if a graph represents a function or not, it says that if we draw a vertical line anywhere on the graph, it should only pass through one time. If it passes through more than once, then it is not a function. So let's show a situation here. What if we were to draw our vertical line through the x value of -2? We would end up with a problem here. If that line crossed through the top function there and it crossed through the bottom function here, then it would not meet the definition of a function because it is crossed through more than once. So there we have a slight problem. So in order to make this graph a function, we need to ensure that the function has only one y value for each different x value. In particular, we need to figure out what to do when x is -2. So here's an idea. Suppose we chose to let the graph of f of x equals 3 go all the way up to x equals -2 and include that x value. That would imply that the graph of g of x equals x plus 2 cannot also go all the way up to -2. However, it could get really close. The way we represent this on the graph is with an open hole. So if we put an open hole at x equals -2 for the graph of g of x equals x plus 2, that would look like this, a big open circle. And then put a closed hole at x equals -2 for the graph of f of x equals 3, does our graph represent a function now? Well, here's how the vertical line test works in that scenario. It's actually only going to pass through once. It's only going to pass through that closed hole. The open hole is just a placeholder. That vertical line is going to go right through it. The function doesn't actually exist there. It's kind of like when we used open holes to represent the shaded region on the number line graph for inequalities. It's like the line is getting really, really close to that value, but it's not actually going to touch it or cross it. So that open hole, closed hole for that x value in the same position is the way to make it so that it's still a function. Now it's time to write the equation for this graph. We know that the function has two different pieces, and each piece will represent one of the functions from above. The only real question is what we should define for the domain of each piece. Domain is what are the x values that that piece exists for. So we're going to fill in the domain based upon the graph that we just constructed. So here we're saying that h of x is equal to 3 if our x values are less than or equal to negative 2, because that's where the x values are shown on the graph when our function is y equals 3. It's for all the x values, not just less than negative 2, but because of the closed circle there, less than or equal to negative 2. Then our function is equal to x plus 2 for all of the x values that are greater than negative 2. I'm going to transfer that right over here. Notice how it's just greater than because of that open circle there. It's not greater than or equal to. So again, this little piece here at the very end is called the domain. And the way this is written, the h of x in the very front is kind of like y equals. We only write that once. And then you can see that the format of the other two functions listed out on the top and bottom next to that little curly bracket. So now we're going to construct a few more piecewise function graphs using the ideas, the strategy that we just talked about. So in this next graph, we can see that there's going to be two pieces. F of x is equal to 2x plus 1 for x values that are less than negative 3. On the other side, f of x will equal negative x for x values that are greater than or equal to negative 3. So we're going to start by looking at this piece first. This is telling us where the boundary will be between the two parts. And what I would actually like you to do is start by drawing a vertical dotted line through the x value of negative 3, just to show that that is going to be the separation between the two sides. And we're going to do a little bit of labeling here. So on the left side of the boundary line, let's write this is where x values are less than negative 3. On the other side, this is where x values are greater than or equal to negative 3. Then we're going to look at the functions, and we're going to write what equation goes on what side. So starting on the left, y equals 2x plus 1 is the piece that's going to go on that side. And then on the other side, we have y equals negative x for the piece that's going to go on this side. Okay, we're going to need our eraser again for this because we are going to need to do some erasing. But the idea is that in this first section on the left-hand side, I'm going to use my highlighter here, the piece of the graph that's going to show up on that side comes from y equals 2x plus 1. So we're going to graph 2x plus 1, and we might need to use our eraser to erase anything on the opposite side of that boundary so that it's only showing up in the highlighted region. So to get 2x plus 1 graphed, we know that it has a slope of 2 and it has a y-intercept of 1. So normally, when we know the slope and the y-intercept, we're going to start at the y-axis. At this point, it doesn't matter that the y-axis is on the wrong side because we're going to go back and use our eraser. So let's go ahead and start by plotting the y-intercept of 1. And normally when we have a slope of positive 2, we're going to go up 2 spaces over 1 to the right, up 2 over 1, and so on. But if we continue doing that, we're just going to get more points on the wrong side. We actually want to get it over here on the yellow highlighted side. So let's actually just continue that pattern in the opposite direction by going down 2 spaces over 1 to the left. See how that's still on the same pattern of the line. Down 2, left 1, down 2, left 1, keep going, down 2 spaces over 1, down 2 spaces over 1. Perfect. Okay, so now what we're going to do, I'm going to grab my line tool, and I need to make a few adjustments here to my line. I'm going to only connect the points starting at the boundary line, going through the points to the left to get that line to show up in that yellow highlighted region. I'm actually going to take my eraser now, and I'm going to erase the other points. We don't need them anymore. We only needed them to help us figure out where this little piece would be. Now the final thing we're going to look at here is the fact that this is x values less than negative 3, not including negative 3. So that means that right here on the boundary line, we're going to have a big open circle. So there's that first piece. All right, I'm going to bring my highlighter back to show that now this is the other side. And on this side, the line that we're graphing is going to be the line y equals negative x. Let's talk about that line. It's going to have a slope of -1, and it actually has a y-intercept of 0. Imagine that it's a plus 0 on the end. If you don't see a y-intercept, it's a y-intercept of 0. So let's go ahead and start at the y-intercept of 0. This time the slope is negative, so it's going to be a decreasing line. So we're going to go up 1 space, but then over 1 to the left, up 1, over 1, up 1, over 1. I'm actually going to stop right there because I've got to the boundary line, and I don't want this line to be drawn where it's yellow. I only want to draw it on the side where it's blue. So that should be enough points to get an idea of what our line looks like. So let's go ahead and connect it all the way to the edge here, just in that blue region. And because this was x values greater than or equal to -3, right here on top of the x value of -3 at the boundary line, we're going to put a big closed circle. So that ensures that this is the graph of a function, and there we have the graph of our piecewise function completed. All right, so the last thing we're going to answer here, it says using the graph, we're going to evaluate f of -4 and f of 5. Now normally when we see this notation, when we've done it in the past, we've thought, okay, we're going to look at our equation, we're going to plug in -4 for x, or we're going to plug in 5 for x and simplify it down. But rather than using the equation, it's actually much easier to just look at the graph when it's a piecewise function, since there are two parts. So all this first question is asking, it's just asking us to find the y value when x is -4. So we're going to find -4 for x, and if we go down here, we can see that the y value is -7. That was very quick. The next one is asking, what is the y value when x equals 5? So we're going to go to the x value of 5, go right down here to our graph, and we can see that that has a y value of -5. Now taking a look at this next example, we can see that the boundary line is going to be at x equals 0, which is actually right on top of the y-axis. So to draw a dotted line through x equals 0, I actually like to draw these like slanted lines so that we can see that showing up there. And we're going to do our labeling the same way. So on the left side is where we have x values that are less than 0. On the right side is where the x values are greater than or equal to 0. Writing the equations, so on the left side we have y equals -4, that's going to be a flat horizontal line through -4. On the other side we have y equals 3, another horizontal line. So for the left side first, I'm going to grab my line tool and we'll go ahead and draw that horizontal line through the y value of -4. And because it's x less than 0, not including 0, we're going to have a big open circle there. Hopefully you can see that. And then on the other side, we're going to have y values at 3. So let's draw that flat horizontal line through y equals 3. And we'll go ahead and draw the big closed circle right there. So that's it. We could put some arrows on the ends there to show that it's going to continue to the left and the right. And right over here, we have a similar question that we answered the last time. So f of -1 is asking what's the y value when x is -1. So if we find that, when x is -1, the y value is -4. And then when x is equal to 0, we are going to choose the y value that has the closed circle. So the y value is 3. We don't want to say it's -4 because it doesn't actually exist there where the open circle is. So if this is an x value that's on top of the boundary line, always look at where the closed circle is to get your corresponding y value. All right, this next graph actually has 3 pieces. We can tell because there's 3 equations here. And so we're actually going to have 2 boundary lines. We're going to have a boundary line at -4 and another boundary line at 1. So let's go ahead and draw in a boundary line through -4, and then we'll draw another one through +1. Okay, so we're going to do some labeling here. So on the far left, that's where x values are less than or equal to -4. The equation that goes with that part is y equals -x minus 5. In the middle part here, this is where x values are in between negative 4 and 1. So greater than negative 4 at the same time less than 1. And the equation for that part is y equals 0. On the far right, this is where x values are greater than or equal to 1, and the equation that's going to go with that part is y equals 1/2 x minus 3. Okay, so let's start to think about the parts. The very first section, I'm going to use my highlighter again. So the section that's here in yellow is where we want the graph to show up for y equals negative x minus 5. So this one has a slope of negative 1. It has a y-intercept of negative 5. Make sure you have your eraser because we're going to start at the y-intercept of negative 5, and a slope of negative 1 means we're going up 1 over 1 to the left. So I'm going to plot these points all the way to the edge of my graph. But I'm only going to connect them in the yellow shaded region, so everything to the left of that boundary line. Grab your eraser. We're going to go back and erase these points here that we no longer need. Now, because that says less than or equal to negative 4, we're going to go ahead and do a big closed circle there. You can also put a little arrow right there on the end. Now, for the middle section, y equals 0. Hey, that one has a slope of 0 and a y-intercept of 0. So it's actually a flat horizontal line that's like right on top of the x-axis. And so it's going to look something like this. And if we think about the types of circles at the end, because it's like greater than, less than, it's not, or equal to, we're going to do open circle here and an open circle there. All right, now for the last section, let me get my highlighter again. Okay, so this section here that's in blue, I didn't highlight the middle section. That one was just so quick. For this last section, it has a slope of 1/2. It has a y-intercept of negative 3. Make sure you have your eraser because we're going to start in a non-blue section. We're going to start at the y-intercept of negative 3, and we're going to use our slope, positive 1/2, so we're going to go up 1, over 2 to the right, up 1 over 2, up 1 over 2. I'm going to do that all the way to the edge. Now I'm only going to connect that line in the blue section, so just on the right-hand side of that boundary. I'm going to put a little arrow there on the end. I'm going to go back and erase this point that I no longer need. And because it's greater than or equal to 1, we're going to do a closed circle right there. So that's how it could look if it has more than 2 parts. Using the graph to evaluate this, when x is negative 3, I'm going to find that here on the graph. We can see that the y value is 0. And when x is positive 2, we can see that the y value, that would be right here, that y value is negative 2. So those last little questions there just work the same way. All right, this very last problem, the graph is given to us. We are going to come up with the equation. So I've used my highlighters here to show that we have these 2 pieces, and we're going to figure out their equations and figure out what is the domain, what are the x values for each part. So for the first line here that's in yellow, we can see that it has a y-intercept of 1, and if we look at the slope, it's up 1 over 1, up 1 over 1. So it's going to have a slope of 1x, or you can just write x, and it has a slope of 1. It also has a y-intercept of 1. Now, thinking about the x values, it looks like it exists for x values less than 2, because it's on the left side of 2. If we were to put in a boundary line, it would look something like this. Okay, now for the other side, the side here that's highlighted in red, this is a flat horizontal line. It goes through the y value of 3. So the equation is y equals 3. We're just going to write 3. And that is if the x values are greater than 2. Now let's think about the open circle, closed circle situation. It's not clear here what is the open circle and what's the closed circle. Because the lines are connected right there, we're assuming that one of them is an open circle, the other one is a closed circle that's on top of the open circle, and that's why it looks like it's connected. We don't want to have 2 closed circles because then it's no longer a function. So the truth is that you get to decide which one is the closed circle and which one is the open circle. Just make sure that you have one of each. So here's one possible way we can say that, but you could have done it the other way as well. So that's only if it looks like the two pieces are connected. Now finally, using the graph to evaluate this, when x is -5, that's right here, we have a y value of -4. When x is 8, we have a y value of +3. And that's how we can graph and deal with piecewise functions.